Hey everyone. So today I'll be presenting this paper. The title is AlphaEdit, Null-Space Constrained Knowledge Editing for Language Models. And the way that I found this paper is, I don't know if ICLR is finished and it was just last week or if it's also this week. But so one of the three big machine learning conferences is going on right now. It was in Singapore. And this paper won an outstanding paper award, which is quite an achievement. I think it's one of three papers. And I didn't look too much into the other two papers, but when I saw this one and the title, I was like, oh, this sounds really interesting. And in my opinion, it is a very interesting paper. One sec. What is this paper about before we start going into a lot of stuff? This paper is about teaching a language model new things, and specifically new knowledge like new facts. So maybe the model was trained in 2020 and it thinks that Joe Biden is still president. Or was Trump president? Anyway, let's just say he thinks that it was trained in 2022 and it thinks that Joe Biden is still president. And you want it to update its knowledge, and this is a paper that discusses how you could do that. And this paper falls under, in my opinion, the field of continual learning, which is when you've trained a model, but then you want to continue to train it with new information. And if you look into that field, there's this fundamental trade-off between learning new information and remembering the information you already know. And most of the papers that exist in this field are about that topic. And that's what this one is about too. And so what it does is it comes up with a very clever way of actually kind of not having to make this trade-off, like making this trade-off disappear. It doesn't disappear completely, as we'll see in the results. And I don't think it makes it disappear completely, but it does. It tackles it in a very clever way. So maybe I'll start with, I just want to talk about what like a null space is, and then we'll go through the paper. Or should I? Yeah, let's do that. Let's talk about what a null space is really quickly. Just so you maybe so I can introduce the concept a couple of times, and because it's a fundamental concept here. So where is it? Okay, it's a really basic idea, which is, say you have some matrix A, and you have over here it's saying B, but it could be a vector. So instead of it being another matrix, it could be a vector, and you multiply that A by B, and you should get a matrix of all zeros. That means that the vectors in B are in the null space of A, which means that that means that they all get sent to 0. And depending on how much you know about linear algebra, what that means is that all the vectors in B are eigenvectors of A that have an eigenvalue of 0. And I know this, this is a very, the reason why this idea is fundamental to the paper, and I think it's super cool because this is something you learn in your third week of linear algebra, your fourth week of linear algebra. I don't think anyone thought of it. Well, there's a paper that inspired this paper, but I don't know, maybe, yeah, this paper over here, Wang et al. 2022-21. But this is a very basic idea that works perfectly in this situation, in my opinion. So I just feel like it's one of those cases where, in hindsight, it's obvious, but it probably was incredibly hard to figure this out. So anyway, this is the key concept behind the paper, and we'll go into later why it's the key concept, but it's this idea of that there's a null space of a matrix, which is a part of a matrix that gets projected to 0. Any vectors that are part of its null space, when you multiply them by the matrix, they get projected to a 0 vector. Yes, okay. Now let's start going through the paper. Okay, So I'll just use the abstract as a way to introduce the paper. So the paper is saying like LLMs often exhibit hallucinations, producing incorrect or outdated knowledge. And in order to fix this, one of the techniques that people are using is what they're calling model editing methods, where you're trying to update knowledge in a targeted fashion. So you want to say like, I want these facts to be updated or added to the model without affecting what the model already knows. And there's two ways of doing this. It doesn't say that in the abstract, but there's two main ways of doing this. One way is to add additional parameters to the model, and the other way is to edit the parameters within the model. This paper is focused on editing the parameters within the model and not adding additional parameters to the model. They say, like, very briefly that this is because adding parameters to the model adds memory, like increases the memory footprint of the model. But honestly, I don't really think it matters that they're only looking at this one method because of the novelty of the approach. So they're focusing on this situation where you want to learn some new knowledge and you want to update the parameters in the model to do that. And the way that the basics of all the approaches that are there that do this is they first locate the influential parameters. Usually it's like a specific layer, like which layers are most important to learning this information. And we'll go into how they do that later. And then they edit that by introducing what they call a perturbation, which is like a small change in the direction of what you want the output to be. That's what all the methods, like the baselines that they look at, do. And their key idea is that they project these perturbations, so like the updates they want to make to the model to learn new knowledge, into the null space of the preserved knowledge. So the knowledge is already known by the model. So this isn't the null space of the like weight matrices in the model. It's the null space of the preserved knowledge, which is this really interesting concept to me, because I'll show you how it makes sense later. But it's like the idea is like, let's add knowledge to this. I think the kind of wrong but correct good intuition for it is we find a part of the model that is or a way of expressing new information that doesn't hurt the model's ability to express the information it already knows, because it's not like it's said in a different way. Man, I won't say it's said in a different way. And the cool thing is, if this idea isn't only the other thing about this is this idea isn't only cool. If we look at the results, you see great results. And the difference that they claim, they can say a lot in the paper that the improvement is only with a single line of code, where they just basically update a part of the algorithm, like one of the equations, the algorithm. In my opinion, that's not true, because you have to do some like other basic linear algebra to calculate to come up with a matrix that a matrix that well, basically to determine, we'll say like to determine the null space of the model's preserved knowledge, and we'll go into how that's calculated later. So, okay, there is a single line of code, but there's also like another step that involves some pretty heavy calculation, matrix like linear algebra to be able to make it a single line of code. But as we'll see later, it's not a big deal, like that there's this additional step because you only have to do it once. So they, another method that they talk about for learning new information is they say fine-tuning is another approach, but it's time-consuming and resource limited. So fine-tuning was the first, and now they're looking into the model editing approaches. Okay. Yeah, let's go into the preliminaries. Is there anything else I want to say here? No. No. I think that's too complicated. So For let's go through the preliminaries because they form the basis of the whole approach. And so they give like a simplified set of equations, or like a abbreviated set of equations for a single layer of an LLM model. So H is your hidden representation, and it's showing you how you calculate your hidden representation. And for those who don't know, language models are composed of feed-forward layers, and which is like a normal neural network, like an MLP, where you have like linear layers with an activation function. Usually there's like a normalization function, and then you have attention layers, and usually they're stacked on top of each other. So you calculate your attention, you have the output of your attention layer, and then you have your linear layer. And what you see here is that they add both the output of the linear layer is M, and the output of the attention layer is A, and they add both of these to the hidden representation to calculate the next one. But all of their work in learning new information is actually focused on learning this, updating this matrix here, W out. And it says over here, this is the reason why. It says, it is worth noting that this weight matrix within a fully feed-forward network, sorry, is often interpreted as a linear associative memory functioning. As a linear associative memory functioning as a key value storage for information retrieval. So the idea is that like this is the memory of the model. This W out is the memory of the model, and what you do is you calculate this for like each of your points. You calculate a key with this thing here, and then by multiplying your key by W out, you can like extract with varying amounts, like very different pieces of information from this memory matrix. So this is a really key idea here, which is that this part of the, oh, sorry, I don't want to do that. This part of the feed-forward layer is the key, and then your memory is WL out, and then what comes out of it is like the information you've retrieved from your memory bank in this matrix. As I say, this is an interpretation. It's introduced in this paper. We'll see how, we'll see how that works down the line. Okay, so how does it work? Or like with this information in mind, how does it work? So what you could say is that you have a set of facts, K1 through U. It says, where's U introduced as a, I think it's down here. Yeah, you have U, new, K, V pairs, where K and V encode your key and then the new knowledge. So you have these like Ks and then these Vs. And the idea is that like the Ks indicate the knowledge that you want to receive, and then V indicates the knowledge that you want, like sorry, this is the search query for the knowledge you want to receive, and V is the knowledge you want to receive from W out. And your goal is to calculate like a perturbation, which is this large delta, such that like K1 times this is equal to V1, or like you want to minimize the difference between those two. So I don't know what, for me, one thing that was really confusing for a long time about, or not for a long time, but like when I first read this, I was like, this is confusing. It's like, where isn't V1 just K1 times W? Because that's what it is over here. You can see in equation 2, like K times W out is equal to V. And I didn't say this before, but W out is just abbreviated as W from now on. But so I was like, so shouldn't they always be equal to each other? But that's actually not the case. So V1 over here, which is like the new knowledge that you want to have extracted, is not the output of this layer. It's not ML over here. V1 is actually a target that you calculate that's different. And the way that this target is calculated is that what you do is you say like, okay, I'm going to go up to layer L, and I'm going to I'm going to calculate. How is it? Something. It's like I'm going to calculate. Sorry, I want to say it correctly. I think what they do is they do a forward pass where they calculate the output V over here of layer L, and then they actually do gradient ascent or descent depending on the objective to like maximize the likelihood of generating the correct next word in the sequence. So you might have like an entire sentence that you want to generate, and it's a new fact. And so what you do is you like calculate the V that would be such that like the subsequent layers would calculate the right representation such that you could generate the sentence that you want to generate. Hope that makes sense. But so V1 is not equal to the output of this layer. It's something different. And that's why you're trying to calculate the, yeah?
So if I understand this correctly, the V1 is like the state of the output of that layer, as if the model already knew the knowledge.
Yeah. Or
okay,
a guess of what that should look like based on using gradient descent to calculate it.
And that can be done because they have access to the new knowledge they want to insert.
Yeah, they know exactly what facts or information they want to insert.
Okay, right, I understand.
Yeah. So throughout the paper, K1 and V1 are new knowledge. And if we go down here to equation 5, K0 and V0 are old knowledge. So when they're calculating the perturbation, they actually want to calculate it such that you want to minimize the difference between both of these, because if there's say that you are able to learn the new knowledge, but there's a huge error here in the old knowledge, so there's a big difference between these two things, then what that means is that you won't be able to correctly generate the old knowledge. So you actually want to minimize the L2 distance between both of these, or the error between both of these. Yeah.
So in equation 5, the only variable you can control is the W, right?
It's the delta, actually. You can't change the W.
It's the delta. So you're trying to find a delta that will satisfy both the old knowledge kind of situation and the new knowledge situation, such that the new knowledge does not affect the old knowledge in a wrong way.
Yeah, so like the update doesn't change the knowledge that you, like it preserves your knowledge of the old knowledge you have in the LLM.
Yeah, that makes sense.
Yeah. So that's why you have both of these in the objective. And when you do that, you can do some fancy math that's talked about here to calculate exactly what this objective is. It's this equation here. So you calculate it in closed form without having to do any kind of optimization, and you can figure out what it is. But you can see here that there's an obvious trade-off between these two, which is that maybe it's not guaranteed that you'll reduce the error in both. In fact, because you know V naught is actually equal to W times K naught, you will always increase the error in terms of your old knowledge this way. So this is how people have been doing it when they're doing model editing, where they're updating parameters. And then let's go on to what they're suggesting that you do instead. Okay, so we talked about before this idea of null space and what it means. It means that when you multiply B by A, you get a zero matrix. And the key insight that they have in here is that they take the perturbation that they were going to update the weight matrix by and then project it into the null space of your K naught, which is your search queries for the old knowledge. So you want to make sure that when you get the old knowledge, you get the same output. Yeah, Arvin?
One question. This null space wouldn't be normally expected to be very small.
Yeah.
Wouldn't it mean that the rank of the matrix must be not full, but that is almost unlikely to happen just by having random vectors, right?
Yeah, true. So they don't actually talk about this, and that was one of the questions I had as well. My other one was like, what if you have competing information? Like, you know, you have a fact that conflicts with a previous fact that you're trying to preserve. So I think here in the paper in general, they don't talk about like the size of the null space, and I think they just kind of, they never really mention it, but they're saying the whole assumption of the paper is that there is a large enough null space because everything's predicated on that. But yeah, it could be quite small. I actually think that's like a really interesting question, is like, if this is a way of measuring how much information a model knows, then like it could be really interesting to, maybe we can come up with like closed form ways of, or some ways of approximating how much information it's possible to put into a model.
Yeah, that sounds very interesting, actually. Yeah.
Yeah. And I'm sure it's not as simple as that though. Like maybe some information is harder to learn than other, but anyway. So yeah, they don't talk about the size of the null space, but that's a really good point, that maybe it's full, especially like, so you do this for millions of times, because you'll see in the objective that the null space should be getting smaller as they keep learning new things. So if the idea is that like they take the original perturbation here, and they project it into the null space, and what that means is that like this is the new way of calculating over, if you see on the left hand side, the V naught, the old knowledge that's been extracted. And you can do like the simple matrix algebra when you know, since you know that like delta naught, delta, whatever that is, like the delta dash is a in the null space, you know that when you multiply it by k naught, you get a zero matrix. So that means that you automatically will get the previous matrix. So this means that like if you can make all your updates to the model in the null space of k naught, then you don't have to make that trade-off. You can learn new information without sacrificing your ability to look up old information. And so also, I just wanted to point out here that, so the null space of k naught is your null space of preserved knowledge, which is interesting because k naught is actually like something, it's not a fixed parameters of the model. Instead, it's like something that's calculated based on the input of the model. It's inputs dependent. But that's how, that's K. So K naught is kind of your preserved knowledge in this case, if anyone's wondering. Okay, so let's talk about how they project the perturbation into the null space of K naught. It's down here. So I don't know if anyone was wondering this, but like another question I had when I was reading this is like, how do you calculate K naught? Because K naught is supposed to represent all the knowledge that the model already knows. And so they say, like, obviously in the paper, they say, obviously we can't like test and find every single fact that this model knows. So instead what they do is they choose like 100,000 sequences that the model generates correctly, that I guess probably are some facts that are of high importance or something. I don't know how they choose them. And that's what their K naught is and their V naught is. It's a batch size 100,000. And so this is an approximation of the total knowledge known by the model, which is infinite in theory. And then what they say is like, we have a matrix K naught that is D naught by 100,000. So they have a matrix of this size, and they want to know what the null space of this matrix is. D naught is probably like between 1,000 and 10,000, so it's a lot less than 100,000. So what they do is they say like, okay, we can do some really simple things since we know linear algebra, which is that we can adopt the null space of the non-central covariance matrix, or just the null space of this, K naught times K naught transpose. And this is a square matrix of size D0 times D0. So this matrix is much smaller, meaning it's easier to calculate the null space. And they can show us, I think in Appendix B2, that the null space of K naught is the same as the null space of K naught times K naught transpose. So first, they make it a lot easier to calculate the null space. And then what they do is they use SVD to calculate the eigenvectors of the and eigenvalues. So since it's a non-central covariance matrix, I think that means that like SVD calculates the eigenvectors and eigenvalues of the matrix K naught times K naught transpose. So U is your eigenvectors, and L lambda, large lambda, is your eigenvalues. And so if you remember what I said before, if a vector times a matrix equals 0, then a 0 vector, then that means that that's an eigenvector of the matrix, and its eigenvalue is 0. And so vectors that are in the null space of a matrix have an eigenvalue of 0. So what they do is they say, like, okay, let's just take the part of U where the vectors in U, the eigenvectors in U that have an eigenvalue of 0, and then we'll make a projection matrix out of those using this like equation 9. And that means that like we can just take the perturbation that we originally calculated, multiply it by P that's been calculated in equation 9, and then we know that the perturbation is now in the null space. Couple of steps. I think it's, like I said before, I think the thing that's really cool about this is all of this is like, I don't think it's basic, but like if you take a linear algebra course, this is some of the first stuff you learn. So I think that's cool that we're just using some of the first stuff you learn in such a cool way, and that it has, you'll see in the results, it has a big impact. So that's how you calculate this projected perturbation. It's just shown over here. And one thing I just wanted to say for anyone who is wondering is that they point out that like it's really rare for there to be actual eigenvalues that are 0 in practical application. So what they do is they just, any eigenvector who has a corresponding eigenvalue less than 10 to the minus 2 is considered to be 0. And that's how they calculate the projection matrix. Which is why probably we'll look at the results and you'll see that it doesn't completely preserve the old knowledge. But anyway, that's how they do it. So yeah, that's kind of the whole, and I'm not going to go through all this math, but basically what they show is like, okay, this is the new update. This is the perturbation that we'll do based on knowing P. So the thing that I was saying is like, I just told you all the steps that you need to calculate P. To me, they say like the one line of code update is like, instead of doing, if you remember the preliminaries, we update the model using this equation 6 and W. So we do W equals W plus this big delta. And now they're saying instead of using equation 6, we'll just use equation 14. And we're all good. And so it's just a single line of code that you're updating. And so it's really simple. But you actually have to calculate this projection matrix P as well, which I consider another step that's not one line of code or like more lines of code. One thing I'll also say, just touching on, oh yeah, go ahead, Dwayne.
Do they have to calculate this projection once, or do you have to do it repeatedly during training?
Yeah, great question. So the answer is that you have to do it once. Because since you're trying to preserve the knowledge that already exists, you're not like like that shouldn't change. Like the knowledge that you're trying to preserve should always be preserved. So that means you just need, and that so that matrix shouldn't change, or it should be the same as much as possible.
Yeah, great, thanks.
Yeah.
I'm curious because obviously as you're training for the new knowledge, you're adding the knowledge you would also want to preserve that. So
Yes.
So wouldn't the projection matrix then change after every new, I guess, piece of knowledge?
Yeah, great question. So what they do is they add an additional component for each like fact that they train, which is, so you can see like this is the original objective, but instead of using it has this P in it where you're projecting the perturbation, and then this one is to like this is the part of the training objective that makes sure that you're staying near the original information, like you're preserving the original information. And then this part of the objective with KP is where you're trying to preserve that additional information that you've added already. So you don't have to recalculate the matrix, because I think this is equivalent to that, where you're adding this objective in. So you only have to calculate it once, and I think that's why they say it's not a big deal. I kind of agree. Like, okay, at the beginning of training, you have to do some like pretty intense linear algebra, and calculate to calculate this update, to calculate the projection matrix. But you do it once, and you're good. So yeah, that's the whole thing. I'm not going to go through all this math because it's just algebra. Feel free to go through it, and I can answer questions if anyone has any. Now let's go through the results, which are equally impressive part of this paper, because equally impressive part. So as they say, they have a couple of different things that they're trying to test or with their results, and they have the 4 questions here. I really like this approach to writing a paper, by the way, where you have like very clearly what you're trying to show, and then you'll see later on like they have their observations which clearly say what the results are. So I think all of that is great. But I'll just read out the 4 questions. Is how does AlphaEdit perform on sequential editing tasks compared to baselines? Can it mitigate the issues of model forgetting and model collapse? Exhibited in figure 1. We'll go through figure 1 in a second. So that's saying like, so they're not testing it on like, I want to learn a single fact, even though that they're testing it on like, say I want to, and you'll see that they're actually like, what if I want to learn thousands of things? Or like, maybe you're learning 10 facts at a time or 100 facts at a time, but you learn like 300,000 facts or 300,000 sequences. How does it do in terms of model collapse and forgetting? Second one is, how does AlphaEdit edited LLMs perform on general ability evaluations? Does the post-edited LLM successfully retain its inherent capabilities? So we learned this new information. We're probably pretty good at that. We probably have our old information preserved, but like, can it still accomplish tasks correctly well? So, because that's another element that we didn't really talk about, that maybe you still know the old information, but you can't accomplish, like it's not as generalizable. The LLM is not as generalizable. Question 3 is, can AlphaEdit, wait, let me just check the time. Okay, good. Can AlphaEdit effectively prevent the model from overfitting to updated knowledge? Specifically, can the post-edited LLM avoid shifts in the distribution of hidden representations? We'll go through that in 1 second. Oh. And lastly, can the performance of the baseline methods be significantly improved with a single line of code in AlphaEdit? So basically, they take all these other methods, all the methods that do this kind of update, and just use the AlphaEdit update and keep everything the same and see if the methods improve. In fact, they all do, which is really cool. So this is like another thing about this is it seems like a very general method. Okay, I want to talk about the first and third question, which is like, can the AlphaEdit mitigate the issues of model forgetting and model collapse exhibited in figure 1? And then they talk about it here, like, can the post-edited LLM avoid shifts in the distribution of hidden representations? So let's quickly look at that so you guys can get an idea of what that means. It's shown here. So what they mean by that is, so they assume that like when you calculate the hidden representations of the specific layer that you're going to be editing, like those 100,000 facts, you calculate the representation of each of them. That once you're done learning this new information, they should be in about the same place, or at least the distribution of those facts should be the same as much as possible. And so what they're showing here is like and they're projecting this into 2D so that they can visualize it, because these representations are like thousands of dimensions, not two. But what they can show here is like some method that does model editing versus AlphaEdit, and you can see like after editing, there's a kind of, you could argue like a clear shift in the distribution where like the pink looks a lot different than the green. And then if you look in the AlphaEdit case, they look pretty similar. And they argue that that's a good indication that you haven't really edited the preserved knowledge that much, because that distribution still looks the same in these scatter plots. And they have some other scatter plots which show that, which we'll go through later. But I hope that makes it clear what they mean by distribution shift and like how they're kind of thinking about knowledge being preserved. Okay. I'm not going to go through the actual experiments, data sets. Let's just go through everything. So performance on knowledge update and preservation. So this is saying like, does it learn? And they have like, this is the first table that has all of these results. And let me just zoom out a little bit. They tested on 3 different LLMs, all these different perturbation methods versus AlphaEdit, like model editing methods versus AlphaEdit, and then they have these like 5 metrics, which are I have to go down to tell you what they are because I don't remember. So efficacy, which is efficiency success, so like how often it generates the correct output. Generalization, which is I guess like how often it can say the same thing in a different way. Specificity, neighborhoods, so I don't know what that is. Fluency, generation entropy. Well, this is more like what's outputted make sense, and consistency, like how often does it get the right answer. So it has these metrics which are trying to define like performance. And you can see in all but one case, which is like specificity. What is it? Yeah, specificity. All the models, the AlphaEdit outperforms all of the baselines in each of these different LLMs. Sometimes it's by very little, like in GPT-J, you can see the difference between some of them is quite small. But in other ones, it's quite large, like here for Llama 3, it's quite large. And it just consistently gets better performance. I actually think this figure isn't super telling of the performance of the model of this method. But you can see it says like AlphaEdit achieves superior performance across nearly all metrics and base models. So in terms of knowledge update and preservation and the metrics that are used for that problem, it outperforms everything. And it has like better text generation, fluency, and coherence. So like tick on what it's supposed to do. General capability tests. Let's see where that is. That is, which figure did I show for this? Yeah, it's this one. Okay. So they have these different data sets that they evaluate the models on. So this general capability test is like these data sets, especially like MMLU, are the data sets that are used to evaluate how good a model is usually. So like if you remember I think MMLU specifically is, if you remember, there's this like, it's either like a hexagon or an octagon. It's over here. I can show it to you. This okay, no. So yeah, these are the different data sets that are used to evaluate the model. But MMLU is the one where you see like math, reasoning, language, blah, 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 like that data set, the one that we always see the results for new language models on, that's that data set. But anyway, so what they're testing is like, here's a couple of different methods that are updating the knowledge of in the data in the LLM. And here's the number of facts that we're updating. And like, let's see how the performance goes as we continue updating the knowledge. And for all the data sets, AlphaEdit is the only one that like basically still preserves its performance, and all of the other ones don't, which means that after a certain number of facts, which means it's the only one that can like basically keep the model performance as good as it was while still learning new information. So I feel like this is a really powerful result, because you can see like the results literally drop to 0 for all of the other methods, basically. Just so little from a pretty high number. Okay, so in terms of general like accomplishing tasks, AlphaEdit is good. Then they talk about the hidden representations, which is like, how much does it change those? Because if it changes those, then it's not preserving the knowledge. And you can see again, like different methods versus AlphaEdit in terms of like how they change the distribution. It does look, like qualitatively, it does look like the distributions changed less. So the bottom chart is AlphaEdit, and the top chart is like different state-of-the-art methods for updating the model. So yeah, you can see that it changes for the other ones more. So that's a tick in terms of this way of measuring knowledge preservation, that the hidden representations don't change that much. And then here's another one, which is figure 6, which is like they say, okay, all of these model updating methods, they basically use the same objective function. What if we change that objective to the one that we're using for AlphaEdit, and the update step to the one we're using for AlphaEdit? And like, how does the performance improve based on that, and these data sets where you're testing learning new knowledge? And you can see, so the green is the original performance, like Mehmet without the alpha-edited objective, and blue is with it. So you can see in every case, there's an improvement in performance. Sometimes it's quite large, like Mehmet edited Llama 3 or Prune edited GPT-J. It's like it doesn't even do any, can't accomplish the task. So you can even use this with some of the baseline, as part of some of the baselines that they've created. Here's some other results that are the same. Like if you look at figure 7a, they're showing you like the starred are with alpha edited and non-starred is like the original. So you can see that the performance is like way better with the alpha edit objective for these baselines that they were looking at. Yep. And then, yeah. So it improves on all the baselines. And if you look at the performance difference, sometimes it's quite a bit. Like it can improve any of the baselines. Doesn't really change the representation. I don't find that one. It can preserve model performance as it's learning new information, and you get like quite sometimes quite a big difference in performance, like improvement in performance from using it versus the baselines. So like I said, I think these results are great. Just to finish up, and then we can start talking about this, is then they have their like, I'm not going to go through the related work. They have this like limitations and future discussions section, which in my opinion needs more, because they don't talk about they just talk about the future what more they could do, but they don't talk at like they don't say any of the limitations of this paper. And there are limitations. Like this update, in my opinion, I would be curious to know how much more computation is required to calculate this perturbation than fine-tuning, or if they're equivalent. Because I haven't gone through all the steps that are required to do these model editing methods, but it's both complex and like there's a lot of different steps that are yeah. And so I feel like there definitely must be limitations to this method. So and Arvid, actually, you mentioned one of them, which is like this idea that the null space could become small, get smaller and smaller. It could be small already, and that's not in the paper. They just talk about like what they could do next. So yeah, I think they should have had some limitations in there, but that's my only complaint about this paper. Everything else I think was great. So yeah, that's the paper. Happy to take questions now or just discuss stuff in general. Yeah, Damien?
Yeah, it's not really a question, but more like just curious. curious about your opinion on this. It's like they don't show any experiments about what would happen if like a counterfactual fact was being introduced. So say the model knew that sky is blue, but now we're trying to teach it that sky is green.
Mm-hmm.
I wonder what would actually happen to the distribution on these layers, and then what would be the actual answer that the model provided.
Yeah, that's a good question. I'm not sure. I was wondering the same thing. I'll say this in their defense, which is that I think they're evaluating their model in the same way that everyone else has been evaluating their models for this approach, and they're just showing that it's better. I do think some great future work would be what you just said, but I still think that what they've done is a good contribution. But yeah, that, and then also like trying to figure out how big the null space is, like if there's more information that can be added, I also think would be a good thing to add to the paper. Maybe they're going to do a journal paper on that.
And it's also like the idea of removing information, right? So for some facts, you probably, before even adding a new replacement fact, you'd want to remove the other fact, the original one. So
yeah, and that's actually a hard one too, because it's not clear how you could take this method and use it to forget things. So that's another. I think that's a really interesting line of research. Yeah, David.
Yeah, I was wondering that in the table where they have lots of different scores, there are lines for pre-edited, and the scores were all really rubbish. And I kind of expected the scores for the pre-edited thing to be quite high. So I guess I was a bit confused about what they're actually testing here. Are they testing on the knowledge of these new edited facts, or are they testing on kind of existing performance of the model in a general setting?
So is it this table here?
Yeah, there's lines for pre-edited at the top. And I kind of expected all the edited things to be, I don't know, less fluent, less consistent, less generalizable. But it's suggesting that the edited models have much higher kind of capabilities in those areas, which I thought was a bit confusing. Maybe we're just misunderstanding what they're actually showing here.
Yeah, that's a good point. So I don't know about the general, like at least in terms of the efficacy, that's in terms of the new information. So I can see why that's small.
Yeah.
I'm not sure about the generalization. To be honest, I have to look more at these metrics. I just went through them and I was like, okay, it tells me higher is better, and they seem pretty good. But yeah, that's a good point. I didn't look at the pre-edited and saw that they were so much lower. I'd like to give you a better answer, but my answer is like, I don't know.
No, it's all good. It's all good.
Yeah.
Yeah, that's really fascinating, this paper. I've also found it quite interesting that you have 100,000 facts that go into creating the kind of existing knowledge. And that's, I assume, quite a small proportion of the total knowledge this LLM stores. But it turns out it's quite a good kind of approximation for the kind of the null space of these value matrices, which I guess kind of makes sense. Maybe if you have a sort of good representation of knowledge, then it's likely that if you apply that, then you'll, I don't know, the null space is going to be shared between the whole vector space. So,
yeah.
So maybe that makes sense. But I thought it was interesting that they could use a small subset of knowledge and get a good generalization.
Me too. Because like again, one thing that I thought was really interesting is that the thing I pointed out before about how you're trying to find the projection matrix for K naught, which is this like back thing, which is input dependent. But it's interesting to me because like I said, it's that's a description of what you know already. It would be really cool to maybe do an investigation into like what that looks like. One thing we haven't touched on is that a part of this approach, all of these approaches, is that you have to select specific layers to update. And so it could be that like different layers are important for different facts. So it might not be super easy to compare, like to really understand how the whole preserved knowledge looks like.
Right, yeah, that makes sense. Yeah. And I guess you already mentioned this a little bit, but as they add stuff to the null space, I guess they're filling it up a little bit, but maybe the whole thing's rotating and actually get other eigenvectors to sort of push towards zero, and the whole thing kind of has more space to remember things in areas that are kind of now newly irrelevant. But I guess, yeah, I'm interested to see in future papers if they address that kind of question.
It's definitely the case that like the null space. So if you want to preserve an original knowledge and then the new learned knowledge, that the null space is getting smaller because you're using a projection into the null space of like the preserved knowledge, and that means to calculate the update to the matrix, which means that you're like reducing that you're using eigenvectors that are in the null space to encode new knowledge. So that means that like they can't be in the null space anymore.
Right. Although fascinatingly, they said that actually they're using not things that have like an eigenvalue of 0, but like very small. I guess conceptually that could mean that you're pushing other vectors into that space, and you could have a slightly new sort of post-edited null space that sort of no longer kind of is used. But I assume over time you'll get smaller null spaces, even with that approximation. Yeah, fascinating. Thank you. Thank you. It's really good talk today.
I've got a comment, and that is because they calculate the population of 100,000 facts, and they do that calculation in the beginning, and that's part of this method. You could actually determine when you are starting to fill the null space up, because you will find a time when you are when that starts to degrade, the quality degrades, and that's sort of almost built into this method. All you need is just one step to measure that.
That's true. If you keep track of like the learned facts and the preserved knowledge, and you just like you calculate the projection matrix at the end of that, or no, you just do SVD on that diagonal matrix. I mean that square matrix, and if you see that the eigenvalues are greater than 1 to the power of -2, then you know that are all greater than that. You know there's no null space.
And then you can go into a method of increasing the number of weights or something like that to add space, and then start repeating this. And then also be interested if you did a pass of fine tuning after you've done this for a while and it's starting to degrade. Then does fine tuning through your data set that you've built? Does it clean it up? Does it just do nothing?
That's a really interesting idea, that you could like have a method for automatically adding capacity to your model. That'd be really cool. Like our models scale without us having to decide how large they should be.
And then the next follow-on thought from that is then, can you train a model from scratch using this? So can you just add space add knowledge into the null space until a null space is full, and then you start growing the size of the model, so you don't end up with a model bigger than you need. But I imagine that you could distill down still into a smaller space. So, yeah.
Fair.
Another quick thought is that as let's say you're kind of adding more and more knowledge and your model's getting more full, I guess, you could increase the cutoff parameter that you use to define your null space. And so you can say actually like things that are smaller than 0.05 or something can be part of my null space now. And I guess I mean, just thinking about like how that kind of correlates with how like a brain works, for example. Maybe it's a kind of case of you're getting some knowledge that doesn't seem super important if it's kind of a small eigenvalue, and you're kind of making room for new, more important knowledge. And I wonder to what extent that cutoff affects how much it forgets stuff. Just a thought.
I think that's a really good point and a really interesting idea. I'm hoping that so if you look at sorry, one second. No, it's over here. Yeah. So if you look at Appendix B1, I'm hoping I can just click on it. Come on. Bear with me 1 second. It's not that far down. Okay. If you look at Appendix B1, they describe like the steps that are actually involved in this model editing approach, like the baseline's not the actual one, but it's basically the same. And like I said, it's quite involved. It's not something I think you can easily incorporate into like a large scale training method, but it would be cool, like as maybe this is a new way to like maybe we can make it into a large scale training method. And that could be like a very interesting way of doing future work, or like very interesting future work they could do. Yeah. Great. I'll take one. Let's do one more question, or if there is one, and then we'll stop. Okay, guess not. Yeah, thanks everyone for coming. I hope you found this paper interesting. Take a look at the ICLR papers if you're looking for any cool stuff that's come out. And we'll see you next week.
Cool. Thank you so much.
Thank you.
Thanks, Peter.
Thanks, Peter.
Thank you.